Hello, everyone, and have a great morning. So, welcome to our physical science online learning. So, now we are on our sixth week for the fourth quarter. So, the thing nature of light, the wave nature of light is the topic that I am going to discuss today. So, students, are you ready to learn new things? Yes, that's great. So, let us explore the world of science. I am always excited to be with you today and be a part of your journey in exploring the wonder of science world. I am teacher Evelyn, joining with you today with the science world of the wave nature of light. So before we'll begin, let me check first if you are ready. Do you have your pen and notebook? And of course, the learning modules with you? Very good. Okay, that's great then. Let's get started. So for today's learning objectives, first, define wave interference, diffraction, dispersion, and scattering. Number two, differentiate constructive and destructive interference. And the last, illustrate and explain the double slit experiment. What is electromagnetic waves? So these are waves that are created as a result of vibration. So look at this illustration or this 3D image. So are waves that are created as a result of vibrations between an electric field and a magnetic field. So in other words, electromagnetic waves are composed of oscillating magnetic and electric fields. Okay, so that is the movement. That is how waves is being created as a result of a vibration. Okay. So what is an electric field? An electric field is the physical field that surrounds electrically charged particles and exerts force on all other charged particles in the field. So either attracting or repelling them. It also refers to the physical field for a system of charged particles. Okay? Now, you have here an illustration of the electromagnetic wave. So these are all waves. They all have a wavelength that determines the distance over which their amplitude changes. Radio waves can have wavelengths as wide as your arms and even longer. So while visible light waves have wavelengths as small as a thousandth of the width of a human hair. So try to look at the diagram where you can see different colors. So the colors depend on their wavelength. So the higher the wavelength, the lesser the energy is. So the color, the red color indicate it has a less energy. So you have the radio, microwaves, infrared, ultraviolet, the X-ray, gamma ray, which is the color violet. So if you try to look at the wavelength of the color violet, then the smaller the wavelength, the higher the energy. Okay. So both light waves and radio waves are examples of electromagnetic waves, meaning that they fall on the same electromagnetic spectrum as infrared waves. So the radiated heat you feel from a stove, ultraviolet waves, and microwaves, the radiation that's used to cook food in a microwave. Okay? So the electromagnetic spectrum is the range of frequencies of electromagnetic radiation and their respective wavelengths and photon of energies. So what I told you in the previous slides that the ha the higher the wavelength, the lesser the energy. So the lower the wavelength, the higher the frequency or the energy level. Okay? So you have here from the lower wavelength or the bigger wavelength, you have the radio waves down to the smallest wavelength. So you have the color violet. Okay? So this is the diagram for the double slit experiment. So the double slit experiment is a demonstration that light and matter can display characteristics of both classically designed waves and particles. Moreover, it displays the fundamentally probabilistic nature of quantum mechanical phenomena. So try to look at the diagram. So where can you see the through and the true? So it is on the bottom part of the wave. So the top part of the wave, that is what you call the crest. So from the crest or from the through to the crest, that is what you call the distance from that is what you call the amplitude. From through to through, so there is space there. So that is what you call one wavelength. If you can see another through, then that would be another wavelength. So in that case, if there is another two here, then you have already two wavelengths. Okay? So this is a clear diagram for a double slit. Okay, if you try to look at the direction of the beam gun, electron beam gun. So as you can see, the light passes through the double slit. Okay, two, you have there the two slits and where the electron beam gun or the light can pass through. So try to look at the distribution of the light or the interference pattern on the screen that is being shown to us. Okay, so that is the reflected light. Okay, class, we have here another example for a double slit experiment and representation. So try to look at this 3D presentation or image, how the waves move. So a double slit experiment is a demonstration that light and matter can display characteristics of both classically defined waves and particles. Moreover, it displays the fundamentally probabilistic nature of quantum mechanical phenomena. So, as you can see, you have here one slit, then the first line or the first column. Then, as light travels or passes in the slit, then another two slits. So how the waves moves or passes through the two slits. So waves travel even more. Okay. Yeah, that's it. Okay. Wave interference is the phenomenon that occurs when two waves meet while traveling along the same medium. So the interference of waves causes the medium to take on a shape that results from the net effect of two individual waves upon particles of a medium. Okay? So, interference patterns are not a standing wave. So waves on a string propagate in only one dimension, while the light wave interference pattern exists in three dimensions. So the standing wave pattern represents no net energy flow, while there is a net energy flow from the slits to the screen in an interference pattern. So okay? Light sources of interference. So looking back at your double slit experiment, you observe wave interference when you use a single source of light. And as it passes the two slits, it acts as if there were two sources of radiation. So this is what you call coherent sources, since they are maintaining a constant phase relationship, same as wavelength and frequency. Okay. Light sources for interference. The sources of the waves must be coherent, which means they emit identical waves with a constant phase difference. So the waves should be monochromatic. They should be of a single wavelength. Okay. So try to look at this diagram. How the light moves passing through a double slit, and the movement of the wave is in constant pattern. Okay? So wave interference, when two waves come close to one another, their effects add together. So if the crest or highest parts of the waves line up perfectly, then the crest of the combined wave will be the sum of the heights of the two original crests. Likewise, if the lowest part of the waves, which is called the through, line up just right, then the combined through will be the depth of the two original through combined. So this is known as the constructive interference, in which two waves on the same wavelength interact in such a way that are aligned, leading to a new wave that is bigger than the original wave. Okay, so we have here the diagram for the constructive interference. So you have the wave A plus the wave B, then the result is bigger. New wave. So this wave A plus wave B will produce a new wave which is larger in amplitude. Okay, students, try to look at now the destructive interference. So you have wave A. So wave A plus wave B. So as you look at now, they have the same amplitude and wavelength, but out of phase. So wave A plus wave B, then there is no wave produced. Okay, so double slit interference, as say you have a laser pointer. Okay, try to imagine you have a laser pointer. So a laser is basically just a bunch of light waves that all have the same wavelength and are all lined up with one another. So suppose you place a card in front of the laser beam with two slits in it such that waves can only pass through two spots. Okay? So kung dalawa lang yung spots doon, so doon lang talaga tatagos yung light. Then you have to measure the amount of light that hits the wall on the other side of the room at various points. Okay. So for a clearer diagram for a double slit interference. So laser beam, look at the diagram, look at the arrow, then the light force the split. So you have to consider that there are two slits in this diagram. So light force to split towards the direction of the arrow. Then how about now here? So the opposite wall where the light will appear. Okay, class, take a look on this diagram or this illustration. Same wavelengths and in phase and same number of wavelengths to hit the target. So this is an example of a constructive wavelength or constructive interference. So what it gives you a new waves. So in here, the target where waves will meet and the waves cancelled out. So what do you expect? There will be no new waves form. So if your slits are farther apart, the light waves will be coming from spots that are farther apart. That means that their path lengths will be more different from one another. So giving bright spots that are closer together. Okay, so diffraction pattern from a wide slit and pattern from a narrow slit. So if we compare single slit diffraction to the double slit interference pattern, the spots are much larger and more spread out. So in particular, the center bright spot is much larger than it would be for the double slit with the same width. So we can view diffraction as light spreading. Okay, class? We can view the diffraction as light spreading out when it comes up to a hole or other barrier and trying to get around the barrier. So in the process of spreading out, it interferes with itself to create the pattern of light and dark spots. That is what we call the diffraction pattern. Okay? Now, how about dispersion in prism? So visible light, also known as white light. Okay? So that was presented in the previous diagram where you can see there where which part is the visible light can be seen. So the visible light, also known as the white light, consists of a collection of component colors. So these colors are often observed as light passes through a triangular prism. Upon passage through the prism, the white light is separated into its component colors. So you have the red, orange, yellow, green, blue, and violet, or the rainbow color. So the separation of visible light into its different color is known as dispersion. Again, the separation of visible light into its different colors is known as dispersion. Okay, so this is how dispersion in prisms is being demonstrated. So from the source is the white light, then what happened as it is uh, put in a prism. Okay, so what it produces, you have here the different colors: red, orange, yellow, green, blue, indigo, and the violet. So if we will perform this in our activity, then definitely from white light under the prism, then this is the light that you can see. Okay, so for a clearer view, then you have this picture. So again, white light from the sunlight, then you have here the prism, then what it comes out, then it will give you a red, orange, yellow, green, blue, indigo, violet colors. So this is what happened to the angle of deviation when light is being refracted. Okay. So blue light refracts more than red light due to the difference in wavelength. So this causes blue light to deviate from its original path by a greater angle than the red light, as it is shown in this diagram. Okay, so light scattering. Light scattering is the phenomenon in which light rays get deviated from its straight path on striking an obstacle like dust or gas molecules, water vapors, etc. Scattering of light gives rise to many spectacular phenomena such as the Tyndall effect and the red hues of sunrise and sunset. Okay, so this is the illustration for the Tyndall effect. So what happened to the scattering of light? So you have there the plus light as shown in this diagram. So the plus light is lighted. Then what happened? It will just pass through this solution. As you can see, the light passes through this solution. And of course, it passes to a mixture of water and milk. So this is the Tyndall effect in milk. So the light can pass through in this solution. Okay. So light scattering, Tyndall effect, also called Tyndall phenomenon, scattering of a beam of light by a medium containing small suspended particles. Example, the smoke or dust in a room which make visible a light beam entering a window. Okay, if you can just imagine or figure out, if you sleep, no, if your room has window glass, then as you can notice that the light will just pass through to the window glass. The light will enter in a window glass. Okay, so we get to see Tyndall effect in our surroundings very often. Some of the examples are: when a beam of sunlight enters the dark room through small hole or window, then its path becomes visible due to the scattering of light by the dust particles present in the room. So when a beam of light is projected on a screen from a projector in the cinema hall, it becomes visible. So when sunlight passes through the canopy of a dense forest, it gets scattered by tiny water droplets. Okay, so we have the Rayleigh scattering. So Rayleigh scattering refers to the scattering of light of the molecules of the air and can be extended to scattering from particles up and about a tenth of the wavelength of the light. It is Rayleigh scattering of the molecules of the air which gives us the blue sky. Okay? So this is how it goes. Rayleigh scattering from air molecules. Scattering at the right angle is half the forward intensity for Rayleigh scattering. So the strong wavelength dependence of Rayleigh scattering enhances the short wavelengths, giving us blue sky. Okay. Okay. So class, I hope you have learned something in our discussion today. And probably you can now explain why is it uh, the color of the rainbow is illustrated in that possible color, and of course why the sky is blue. So from that, no, from what we have learned, then you can now explain how the light gives its color. So thank you and stay safe, everyone.